In this video, we will look at set operations. In section 2.2, we define the operation of finding the complement of a set. In this section, we define the set operations intersection and union. In everyday usage, the word intersection refers to the common region where two streets cross, right? We think about out next to campus, we have Cherry Avenue and University. They cross at an intersection. It's the part of the road that is in both of the two roads. The intersection of two sets is defined in a similar manner. The intersection of two sets denoted as follows, right? A intersect B is the set of elements common to both A and B. In set builder notation, A intersect B is the set of all x's such that x belongs to A and x belongs to B. It's where the two sets overlap. If you can find things or elements in both of the sets, we define that as the intersection. We'd like to look at some examples here. Let A be defined as the set 1, 4, 5, 7. Let B be defined as the set 2, 3, 4, 5, and 6. Let C be defined as 3, 6, 9. Find the following intersections. A intersect B, A intersect C. Well, for A intersect B, we're going to find the elements that are both in A and B. To find A intersect C, we will find the elements that are in both A and C. Let's start with A intersect B. Can we find some numbers in both of the sets? A contains 1, B does not. A contains 4, so does B. A contains 5, so does B. A contains 7, B does not. And we're done. A intersect B is the set of two elements, 4 and 5. What about A intersect C? Take a look here at A intersect C. A contains 1, C does not. A contains 4, C does not. A contains 5, C does not. A contains 7, C does not. A intersect C is the empty set. And we can also denote that using our empty set notation with our slash mark through our circle. I'll go to the full screen here to see what we're working with. And there we have it. If we wanted to take a look here, sort of get an idea of what our Venn diagram may look like, let's do it for A intersect B and then allow you to kind of make the determination for what A intersect C might look like. The first circle here will represent the set A. The second circle will represent set B. Now note here that where they intersect is where they are similar, and that's going to be in the middle. And we see here that our intersection is 4 and 5. So the numbers 4 and 5 will go directly in the middle. Now what numbers are in the set A that aren't in the intersection? Well, that's 1, that's 7. Then what about for B? When we look at B, 2, 3, and 6. So here, with the bigger picture, we have our Venn diagram for our two sets A and B. The intersection will be right there where our two sets adjoin or intersect, where they overlap, where we're going to find elements that are in both A and B. So when you hear that word intersection, think about the word and. A and B, numbers or elements that are in A and B, 4 and 5. So we've defined 3 sets here. We have D, E, and F with the following elements. I want to go ahead and find the intersection for each of these sets, right? That is D intersect E, D intersect F, E intersect F. Let's start with D and E. That notation is intersection. We're going to try to find the numbers that are in D and E. D has a 0, E does not. D has a 3, so does E. D has an 8, so does E. D has a 9, so does E. And that's it, right? You can go the other way and start with E and work your way back to D, right? E has 11, but D does not, right? So choosing one, working all the possibilities of that one, you're done. What about D intersect F? D, F have both 0. D has 3, F does not. D has 8, so does F. D has 9, F does not. Lastly, E intersect F. E has a 3, F does not. E has a 4, F does not. E has an 8, so does F. E has a 9, F does not. E has 11, F does not. So there's only one element that is in both E and F. So E intersect F is simply the set with one element, and that element is 8. We have that two sets are disjoint if their intersection is the empty set. In other words, if two sets have nothing in common, we say that those two sets are either mutually exclusive or they are disjoint. Think about that in terms of the medical terminology. A joint is where two bones come together. It's where they intersect, it's where they are adjoined. But if something is disjointed, it's separated. They're not touching, they're not overlapping. So something that is disjointed, there is no overlap. In this case here, we can illustrate that using a Venn diagram where the two circles representing sets do not overlap, meaning that their intersection is the empty set. For example, we have the following sets A, B, and C. We want to find A intersect B. We want to find A intersect C. A contains 1, B does not. A contains 4, but so does B. A contains 5, so does B. A contains 7, but B does not. Here we have our intersection for A and B. Now what about A intersect C? Well, once again, A contains a 1, C does not. A contains a 4, C does not. A contains 5, C does not. A contains 7, C does not. The intersection is disjoint. There is no overlap. There is not a number in one that's also in the other. So we say that their intersection is the empty set. So that's how that works. Two sets are disjoint if they have nothing at all in common. Some examples that we could relate to our previous discussions are dealing with our sets of numbers. Say, for example, the rational and irrational numbers. Well, rational numbers can be written as fractions. Irrational numbers cannot. Therefore, rational and irrational numbers are disjoint. Every number in the rational will not be found in the irrational. They're disjointed. Likewise, our negative and positive numbers. Negative numbers live to the left of 0 on a number line. Positive numbers live to the right of 0. You will not find a number in both sets. Therefore, negative and positive numbers are also disjoint. In a sentence, the word or means one or the other, but not both. For instance, if a menu states that you can have soup or salad with your meal, this generally means that you can have either soup or salad for the price of the meal, but not both. In this case, the word or is said to be an exclusive or. However, in the mathematical statement A or B, the or is an inclusive or, meaning that it could be A or B or both. So the union of two sets, denoted as A union B, is the set that contains all the elements that belong to A or to B or to both. Now consider that union notation is not the capital U like our universal set. We don't want to get that confused. The symbol in between A and B is our union symbol. It's a little bit wider than a capital U, and this represents the union or the bringing together of two sets. So the union means that an element can be in either of the two sets, and in some cases it might be in both sets. So we're just trying to consider everything about A, everything about B. See an example. We have three sets defined, A, B, and C. So we want to find A union B. We want to find A union C. Well, look how simple this is. Let's do A union B first. To find the union of two sets, we're quite simply going to write out every single element that's in A, that's in B. If you put them out of order, that's fine. But again, remember that the rule of thumb is to make sure that our numbers are in order from smallest to largest. As you see, A, B, and C, each of those three sets are in ascending or increasing order. So A union B is going to contain 1, 4, 5, 7, and it's going to contain 2, 3, 4, 5, and 6. Quite simply, anything that's in A, anything that's in B will be in the union as well. So let's define A union B using every number that's in A, that's in B. 1, 2, 3, 4, 5, 6, 7. And now we see that A union C, when combining the two sets 1, 4, 5, 7, 3, 6, 9, placing them in order from smallest to largest. If there's any repeats, we listed only once. Here we will have 1, 3, 4, 5, 6, 7, and 9. Looking here at Venn diagrams and equality of sets, we can use the following figure to determine whether two expressions that involve two sets are equal. For example, to determine whether the following expressions, A union B complement and A complement intersect B complement, are equal for all sets A and B, we find what region or regions each of the expressions represent in the following figure. We see here that if we take two sets and place them within a universal set, that is our rectangle to denote the universal set, we are going to have four separate locations. We're going to have the intersection of the two sets A and B. We're going to have the area of A that's not in B. We will have the area in B that's not in A. And then we'll have the area that is in the universal set that is in neither A nor B. And we will use this along with our following examples to determine if two expressions are equivalent to one another. So the Venn diagram is our visual aid to determine if two expressions are actually representing the same set. To have it written correctly in our notes, we see that the Venn diagram shows the four regions formed by two intersecting sets in a universal set. It shows the four possible relationships that can exist between an element of a universal set and two sets A and B. That is, region 1 may be an element of both A and B. Found right in the middle, that's the intersection. We're going to call that section 1. The second section may be an element of A, but not B. We will refer to the area of A that's not in B to be region 2. Region 3 may be an element of B, but not A. So we see this is the area of B that is not included in A. Finally, our fourth region may not be an element of either A or B. This region will be the complement of A or B. The following exercise: determine whether the expression A or B complement is equal to the expression A complement intersect B complement for any two sets A and B. To get a visual of this, we want to consider now creating a Venn diagram for the left side expression as well as a Venn diagram for the right side expression. And we want to see if those two Venn diagrams represent the regions that will be the same for each. If they are, then these expressions are equivalent. If the shaded regions are not the same, then we will say that these two expressions are not equivalent. We will start with the left side expression. Note that we want to find the complement of A union B. So it suffices to say our first step is to consider what is A union B. Well, it's all the regions of 1, 2, and 3, right? We would shade in both circles A and B to represent the union A union B. Therefore, what is the complement of the shaded region? Well, it's the unshaded region. If we consider the complement of A union B, that is the A union B in parentheses, the complement of that is everything within the universal set that's outside of the circles. So here in this case, region 4 represents the left side expression A union B complement. Now let's go to the right side expression. A complement intersect B complement. Well, let's consider what our region A complement is. It's everything outside of A. That is, these are the regions 3 and 4. Well, B complement is everything outside of B. That is regions 2 and 4. Now consider the intersection. Which of these regions can you find in both A complement and B complement? We have 3, 4 for A complement. We have 2, 4 for B complement. The one that is the same is 4. So A complement intersect B complement is represented by the 4th region. We go back and see, well, that's the same for our previous expression. A union B complement, we now see, is equivalent or equal to A complement intersect B complement. So we can now say that because the regions are represented the same, we have that the two expressions are equal. Let's try a second exercise, and this time we'll give you a moment to now try to pause the video and work through the expressions. That is, on the left side, we want to find the shaded regions, or our Venn diagram that represents A intersect B complement. Then we move on to the second expression, A complement union B complement. Are the shaded regions the same or are they different? Give you a moment to pause the video and we will work together on this expression, and then we will see what the final answer is together. Okay, so we're going to look at the Venn diagram for A intersect B complement. So in this case here, let's think about starting inside the parentheses. A intersect B, what would that look like? Let's go ahead and start off by drawing our Venn diagram with our 2 circles inside the universal set. Going left to right, we'll say that the left circle is A, the right circle is B. As we noted before, the middle region, the intersection, is region 1. The area of A not in B is region 2. The area in B that's not in A is region 3. And as we just saw in the previous example, A union B complement is region 4, everything within the universal set not in A or B. We want to start by finding A intersect B. Well, the intersection is right at region 1. We want to find the complement of this. What is the complement of A intersect B? Well, it's everything else. Well, what do we mean here? Well, if A intersect B is region 1, A intersect B complement will be regions 2, 3, and 4. You can draw a photo. Working off of this one, it was pretty easy to see that if the intersection of A and B is the middle, well, everything else but the middle would be 2, 3, and 4. But we'll draw a picture just to have that image. If I shaded the middle, the intersection of, the complement of that is going to be everything else. I'll shade A, not in the middle. I'll shade B, and I'm going to shade the outside. That is region 4. And only shading within the rectangle is the universe, nothing greater than the universe here in this context. So we see that the only thing not shaded directly in the middle is our intersection. So here, A intersect B, the complement of that, that's regions 2, 3, and 4. Now, what was that last expression that we have? We're going to go back here to the screen, and now we're going to determine what is A complement union B complement. Once again here. We're going to do the same thing, right? So this time we're going to write up here A complement union B complement. Maybe off to the side here to remind ourselves that what we just found for the left side expression was represented by regions 2, 3, and 4. If you want to write that out numerically instead of the Roman numerals, of course, I would encourage you to do that for your notes. You just might see that in the textbook, you will see the lowercase Roman numeral expressions. Likewise, on your homework, you may see the numbers 1, 2, 3, and 4 represented as I, and IV for 1, 2, 3, 4, respectively. So, just going to have that circled as a reminder. We're going to go to the full screen here, and we're going to take a look at this Venn diagram, A complement, union, B complement. Starting off with our Venn diagram itself, we'll draw our universal set, set A, set B, where they overlap. So what do we want to look for here? We'll first want to find what is A complement, what is B complement, what's the union of the two. Well, A complement first off, I'll use this one here. I'll go ahead and draw out B complement as well. So A complement is everything outside of A, meaning that if A consists of regions 1 and 2, I'll do the numbers this time. 1, 2, here we have region 3, and outside we have region 4. So A complement means to disregard A, meaning 1 and 2 are not here in A complement, only 3 and 4. So A complement, regions 3 and 4. Now what about B complement? We'll take everything out of B. All right, well, first off, region 1 in the middle, 2 to the left, 3 to the right, 4 on the outside. If B consists of regions 1 and 3, B complement will consist of regions 2 and 4. So B complement, regions 2 and 4. We want these two things brought together. We want the union of A complement, B complement. A complement, union, B complement. Well, drawing the picture, we're going to get to that in a moment, but just use the regions now. We're going to unionize things. We're going to bring everything together. So we're going to bring together these regions. In this case here, we have 3, 4, 2, 4. 4 is repeated. We're only going to write it once. 2, 3, 4. And when you know it, regions 2, 3, 4. Regions 2, 3, 4. So we'll see here that A complement, union, B complement share the same characteristics, same regions as A intersect B complement. So we're going to get the same depiction as well. In essence here, everything is shaded except the middle, except where they intersect. 2, 3, 4. So here's shading region 2, shading region 3, shading region 4, leaving out the middle where they intersect because that's region 1. So once again, right, just as before, we now can verify, going back to the full screen, determine whether these two expressions are equal. And we just did that. We just showed here using our Venn diagrams that they represent the same regions, that is regions 2, 3, and 4. So these actually come from what are called De Morgan's laws. De Morgan's laws show us a special relationship between one single union and one single intersection. Think about what we just said there, right? We're taking a look at De Morgan's laws. It says A union B complement is equal to A complement intersect B complement. We just saw that, right? And it's stated as the complement of the union of two sets, that's the left side, is the intersection of the complements of the sets. Likewise, we have here that A intersect B complement is equal to A complement union B complement. We just found that out. And we can state this as the complement of the intersection of two sets is the union of the complements of the sets. De Morgan's law shows us a way to express a union and an intersection equal to one another. Make sure that we have this noted as we've walked through our visual proof for De Morgan's laws. These two need to be memorized, so much so that not we aren't memorizing them because we need to, but because we've practiced this one now, and now we want to be able to regurgitate it as easily as possible for any future logic course you may take. De Morgan's laws, very useful for us as it shows the relationship between a union and an intersection. Our next examples work with expressing our set notation in sentence form. That is, write a sentence that describes the set. And when we think about this here, every time you see the union notation, think or. When you see the intersection notation, think and. And when you see the complement notation, that is the apostrophe, think not. That is, the element is not in K. For part A here, we have the expression that can be stated as the element is in A or the element is in B and C. Let's see that right now. The set of all elements that are in A or are in B and C. Right? If it's in the intersection of B and C, or if it's in A, we can say the elements that are in A or the intersection of B and C. Part B, we have that the element can be in J and not in K. That is, J intersect K complement. It's in J and it's not in K. You see some more expressions here. D intersect the union of E complement and F. That is, the element can be in D and the element is in F or E complement. That is, in F or not in E. Part B says the element can be in M or not in L. We see the union notation. We can swap that around. We can say the element is not in L or the element is in M. We can read that as the element that's in M or the element that's not in L. We go to our next example here that shows a Venn diagram involving three sets. The Venn diagram in the following figure shows the 8 regions formed by 3 intersecting sets. It shows the 8 possible relationships that can exist between an element of a universal set and 3 sets A, B, and C. Now consider why we might have 8 elements, right? Why would we have 8 relationships? Well, we now have the possibility of the element is either in or not in the following set, and we have 3 sets to work with. That is, if you have 2 options in 3 sets, well, 2 times 2 times 2, or 2 to the 3rd power, gives us 8. That's where our 8 relationships are coming from. That is, region 1 falls right in the middle. It's the intersection of A and B and C. That is, region 1 may be an element of A, B, and C. Region 2, right above, may be an element of A and B, but not in C. Region 3, moving in the clockwise direction, region 3 may be an element of B and C, but not A. Region 4, staying inside, staying within the circle here before we extend outward, we see region 4 may be an element of A and C, but not B. Now to go to region 5, we're going to jump right up, and it's inside A. It's the element of A, but not B or C. Now, clockwise, to B, we have region 6, may be an element of B, but not A or C. Region 7 at the bottom, may be an element of C, but not A or B. Lastly, region 8 is that region that is outside of our 3 circles. It may not be an element of either A, B, or C. It's the complement of A, B, C. We will first look at part A, that is A intersection C. Go to full screen here. Where do we have A intersection C? Well, let's start by labeling out our 8 regions, starting with the middle region. We'll skip the Roman numerals for now and use numbers. That is regions 1, 2, 3, 4, 5, 6, 7, and 8. The reason we don't want to do those numbers, right, is because it kind of looks like that we're working with a universal set that contains numbers 1 through 8. So using the Roman numerals will clear up any confusion of, are we labeling regions or are we actually looking at a universal set that contains these following 8 elements? So that's why we don't do it, but here we have it labeled regions, right? So we know that's what we're working with. So A intersects C, right? Those elements that are in A and C, but not in B. Intersect, so A will intersect C right here. So you see there that for A and C, the regions that they share are 4 and 1, right? We can see that the number 3 is over here. C contains region 3, but A does not contain region 3. C contains region 4, and so does A. C contains region 1, and so does. We'll start here with the first example, A intersects C. Note that we are using the numbers to represent the regions. The reason why we use the Roman numerals is so that we don't mistake and look at this and think that, well, oh, these are actually numbers within a set, right? That this universal set contains the 8 elements numbers 1 through 8. So in this case here, we have it labeled regions, so we know what we're talking about. So A intersects C, right? What are those regions that we can find for both A and for C? If you look right here, right, region 1, exactly where we start with, well, that's the region for A, B, and C. There is, right, region 1 is in the intersection of A and C. And if you want to, it's almost like you could take out B and just consider there is our intersection for A intersects C, right? Right here, regions 1 and 4. I'm going to place B back around here. Now we have A union C, right? That is, what are all the regions for A? What are all the regions for C? Bring them together. And really, before I get going, let's think about, if we skip back here, what are the regions in A? Right? For A, we have 1, 2, 4, and 5. Right? Those are our regions for A. Well, what about for C? C contains the regions 1, 3, 4, and 7. So what's the intersection of those? All right? Where are the regions that are in both A and in C? Well, I have 1 over here. I have 1 over here. I have 2 over here, but it's not over here. I have 4 over here, and I have 4 over here. I have 5 over here, but not over here. Right? I have 3 over here, but not over here. I have 7 over here, but not over here. It's just regions 1 and 4. So that's a way of thinking about doing that. And same for A union C, right? The union means, well, we're going to take these numbers and actually bring them together. So let's do that. We have 1, 2, 3, 4, 5, 7. Lastly, what about A intersect B complement? Now again, if this is more difficult to think about in terms of the image, well, start with A. What's in A? We found 1, 2, 4, and 5. Right, these are the regions, 1, 2, 4, and 5. We want to know, what's the intersection of that with B complement? Well, think about what B is. B is 1, 2, 3, and 6. So the complement of that is everything else. Not 1, not 2, not 3, not 6, but rather 4, 5, 7, and 8. Right, these are the regions for B complement. Because what's in B? 2 and 6, 1 and 3, not down here. We're finding the intersection. So what's in both? 1's over here, but not over here. 2 is over here, but not over here. 4 is over here, it's also over here. 5 is over here, it's also over here. A intersect B complement will be regions 4 and 5. So there we go. A way to determine the intersections and unions, right? The sets represented by our following expressions. Just consider the regions, and then for intersection, what's in both. For union, bring them all together, and you can determine your region. So for each, I'll give you a moment there to draw now your Venn diagrams containing 3 sets, shade the regions, highlight that, right? Note it, label it, title it if you need to have for your notes. We'll go to the full screen again, or rather we'll go to the slide to show each of our shadings. We see here for part A, we have 1 and 4, as we found. For part B, A union C, we're shading everything that's in A, we're shading everything that's in C. So everything except for 6 and 8. Lastly here, for part C, A intersect B complement. Our shading there, once again, represented by our regions 4 and 5. So now you have your visual image as well. What you see there, how we came to that conclusion, just determining the regions for each, finding their intersections, unions, etc. Use our Venn diagram with 3 sets to answer each of the following. Which region represents A intersect B, intersect C? So all the elements that are in both A and B combated with the intersection of C. Well, really, this is what are the elements that are in A and B and C? Well, that's that one in the middle, right? That's region 1. Part A, all we're looking for is the region directly in the middle. What about part B? A union B intersect. Well, we're going to go to the big slide again. A union B intersect. Well, what's in A? 1, 2, 4, and 5. What about B complement? Pause the video at any time if you'd like so that you can not see me work it through if you'd like to give it a go on your own. Well, for B complement, everything that's outside of B. So if we're here for B, we got inside B is 1, 2, 3, and 6. So let's take out of that, right? On the outside here, starting with our smallest number if we can, we have outside of B, 4, 5, 7, and 8. We want the union. So we want to bring these regions together. So let's do that. Well, they have the first region, denoted I. Second region, II. There is no 3, but there's a 4, IV. There's a 5, so it's just V. We do not have a 6, but we have 7, which is VII. We have 8, which is VIII. We will confirm that we will have every region except for 3, except for 6. So let's see what we get here. Going back to our slides. For part B, note here that we have the shading everywhere except for 3 and 6. That is, A union B complement is represented by regions 1, 2, 4, 5, 7, and 8. 1, 2, 4, 5, 7, and 8. Let's take a look at C now. Which regions represent C complement intersect B? That is all the elements that are in B and all the elements that are not in C. Once again, right, start here. Determine, just as we did before, determine the elements that are in C complement, or rather the regions, and determine the regions for B and see where they agree. See which ones that are in both C complement as well as B. Pause the video now if you would like. Go ahead and take a look here for part C. For C complement, everything not in C, well, that would be everything not in C, 2, 5, 6, and 8. Everything in B, 1, 2, 3, and 6. Thus, we want to find those that are the same, that is both in C complement and in B, and we're just going to get 2 regions here, right? Regions 2 and 6. Look at another exercise here with a given universal set, as well as sets A, B, and C. Find each of the following. And we will list out our first 2 examples. We'll find A intersect B, and then we'll find A intersect B complement. With some of the examples, right, we might feel the need that we don't have to create a Venn diagram, and that's true, right? For A intersect B, right, just determining what are the elements that are in both A and the elements that are in B. Well, do some erasing here. And just based on looking at what the problem is, right, now that second example with B complement, I might be more employed to create a Venn diagram because I need now to determine, well, what are those elements that are in the universal set as well, right? Not just in A, not just in B, right? When we say B complement, we're saying, oh, the elements that are in A, the elements that are in C, well, what about the elements in the universal set that might not be in A, B, or C? Right? We have to consider that. But for A intersect B, just consider A as 2, 4, 6. And then looking here at B, we have 1, 2, 5, and 8. So just for this example, A intersect B, I'm looking for elements that are in both of the sets, and I only have a 2. We have one element contained in this set A intersect B, and that is the single element of 2. Now, what about A intersect B complement? This is where I would maybe encourage you to draw the Venn diagram with the 8 regions for our 3 sets. Give you a moment here to pause the video to create the Venn diagram, and I will do so as well, making sure, right, don't leave out those elements that are in the universal set that are not found in A, B, or C. We have our sets listed. We'll go ahead and draw our Venn diagram. Starting with 1. 1 is in B and C, right here. Going with 2. 2 is in A and B, so right here. Going with 3. 3 is only in C. For 4, 4 is only in A. Looking at 5, 5 is only in B. Looking at 6, 6 is only in A. Looking at 7, 7 is only in C. Looking at 8, 8 is only in B. And now we can consider, if we just write out the sets as well, right, do we even need this? I can find A complement just working off of my universal set. A complement, if I need it in the future, which maybe we do for these exercises, let's go ahead and find A complement. Let's find B complement. Let's find C complement. We're just looking at the numbers 1 through 8. 1, 2, 3, 4, 5, 6, 7, 8 are counting numbers. A complement. Well, just don't write 2, 4, 6. Write 1, 3, 5, 7, 8. There is a complement. For B complement, we're just not going to write 1, 2, 5, 8. That is 3, 4, 6, and 7. Well, then C complement, therefore, just don't write 1, 3, 7. That is 2, 4, 5, 6, 8. So going back to our example, right, we're looking at A intersect B complement. Well, we can use the image here, or we can just use our set notation, our roster method, right? Well, A intersect B complement. What's in A that's also in B complement? I have a 2 here, but not here. I have a 4 here and here. I have a 6 here and here. And that's it, right? I have a 7 here, but not here. A intersect B complement will contain the elements 4 and 6. We look at that right here. Where is that? It's right here. A intersect B complement. Everything that's in A, that's not in B. So we just had to essentially kick out that number right there. Kick out the 2. A intersect B complement. Next example, we're going to find the complement of A complement intersect B. Right? Maybe it suffices to say that when we have those parentheses, we could start by the reading on the outside, work our way in. Right? We're complementing something in parentheses. We're complementing the intersection of A complement in B. So maybe where do we want to start here? Well, it would be easier to start on the inside when we do the work. That is, what is the intersection of A complement in B? So we're going to go ahead and write this out. A complement intersect B complement. We have our image to work with, but really I just want to work with our roster methods. That's the easier way. What is inside of our parentheses? We're going to start there. In order to find the complement, we need to find what we're complementing. Right? We want to find the intersection and then complement the intersection. It's logic, right? Don't think about this mathematically. Think about it in logical terms. I want to find the complement of the intersection. So I have to start with the intersection before I can complement it. Intersection, A complement and B. I'm looking at A complement I'm looking at B. What are the same? 1, 5, 8. I want to note that. 1, 5, and 8, well, this is a complement intersect B. I just found what's in parentheses. And now I want to complement that. What's everything that's not 1, 5, 8? Well, that's 2, 3, 4, 6, and 7. We found the complement of the intersection by first finding the intersection of our two sets, then finding the complement of this intersection here. That's the name of the game here. Let's take a look at our next example. We're going to find the union of B and C, and then find the union of A union B or C. So we have a bunch of unions here. We have a bunch of bringing together, right? If I bring together B and C, right, everything that's in B, everything that's in C gets brought together. That's the union. So I have everything that's in B and C. But then what do I do with that then? I then unionize that with A. Therefore, I'm collecting everything that's in A, B, and C. So I'm covering everything that's within our 3 circles. The only thing that I'm not covering, because no complements were discussed, is everything that's outside of our Venn diagram. But consider here, right, that the Venn diagram we created, there is no number in the universal set that isn't found in either A, B, or C, right? All of our 8 elements are found in either A, B, or C. So if we union all them together, A union B union C, well, we're going to find that it's just the universal set. So I want to be able to write this out here. Do some erasing. We're trying to determine A union, and in parentheses, B union C. Well, logic dictates, and mathematically we've been taught to start with parentheses. If I find B union C, I'm bringing together B and C. 1, 2, 5, 8, 1, 3, 7, I'm bringing all that together. 1, 2, 3, 5, 7, 8. But now I'm going to take that expression and unionize it with A. So everything that's in A, 2, 4, 6, is going to be brought together with everything in B union C, 1, 2, 3, 5, 7, 8. I'm collecting everything. 1, 2, 3, 4, 5, 6, 7, 8. So it turns out when I unionize all 3 of these, this is going to happen every single time, right? Because if there was that one element that was floating outside of our 3 circles, then we wouldn't have this case. But in this case, our 3 sets brought together is actually the universal set itself. So just a nice rare case there. Maybe 1, 2, 3, 4, 5 more examples. Take a look. So we're going to get into some more complex notation building here. That is, if you look at the following example, we have, and make sure I'm on the correct screen, we have here the A intersection B union C, and then the complement of that. So once again, right, we have a complement being taken on the outside, but then even on the inside of our parentheses, we have more parentheses. So it suffices to say that maybe we start with the innermost parentheses just as we would with an order of operations, right? Even in this logic set builder notation that we're dealing with, right, building sets, creating sets, defining sets, that we want to think about some of the mathematical rules that we've learned previously, and that is work with the parentheses contained within parentheses, right? And we just found that B union C is everything in B and C. 1, 2, 3, 5, 7, 8. But now we want to intersect that with A, not adjoin it, right? We don't want to bring A together with BUC. We want to find the intersection of A and BUC. So I'm going to go ahead and erase this here to create more space. I'm going to go to the full screen here momentarily, write out what we're trying to determine, A intersect B union C, and all that will be complemented. So we start with B union C, and as we saw in the previous example, B union C, everything in B, 1, 2, 5, 8, everything in C, 1, 3, 7, 1, 2, 3, 5, 7, 8. Now, what if this overlaps with A? A intersect, right? We want to take this set and intersect it with BUC. Well, 2 overlaps, and that's it. So A intersect B union C is simply the set containing the element of 2. I want to find the complement of this expression. Everything except 2. Well, we write that out. 1, 3, 4, 5, 6, 7, 8. Everything that's not in this set is the complement. So we just found the complement of A intersect B union C. Create the roster set. All right, working with sets A, B, and C, find the negations, find the complements to make your work a little bit easier there. And we'll see here, A union C complement, intersect B union A complement. Once again, right, start with the parentheses on the left to find that one set. Start with the parentheses on the right to find that one set. So now you're just working with two sets. Find the intersection of the two sets to find the one set. Give you a moment to pause the video here. So we'll start by finding our two sets in parentheses, A union C complement. A is 2, 4, 6, so we'll end up listing those. C complement is 2, 4, 5, 6, 8, so we'll list everything we see. 2, 4, 6 can actually be found within C complement, right? 2, 4, 6. So A union C complement is just C complement, 2, 4, 5, 6, 8. B union A complement, look at B, 1, 2, 5, 8. A complement, 1, 3, 5, 7, 8. We're going to list them all out. 1, 2, 3, 5, 7, 8. Right? And if there's any error, please let me know in our comment section. Email me there. But just trying to go through that there. A complement 1, 3, 5, 7, 8. 1, 3, 5, 7, 8. B 1, 2, 5, 8. 1, 2, 5, 8. Seems that everything's there. We try to find the intersection of these two sets. For these two sets, what are the same? 1 here but not here. 2 here and here. 5 here and here. 8 here and here. Find the two union sets, intersect the two union sets. You have your set containing the elements 2, 5, and 8. Yeah. Determine whether the following expressions are equal. A union, the intersection of B and C. A union B intersects C. As we saw earlier, we will start with the left side expression, determine the regions that represent the expression, then we will look at the right expression, determine what is represented by the right expression. So let's start with A union B intersects C. So we can determine what's in B and C first, then determine what is similar to A and the intersection. So we'll go to the full screen here. Create our Venn diagram showing the 8 regions. I will use numbers this time because we're working solely with determining regions. Region 1, 2, 3, 4, 5, 6, 7, and lastly region 8. All of those elements that are not found in A, B, or C. So what are the regions for B intersects C? We'll determine, what are the regions for A? The regions for A are 1, 2, 4, and 5. The regions for B, 1, 2, 3, and 6. The regions for C here, 1, 3, 4, 7. To find B intersects C, again, these are regions. I want to note that, right? I'm talking about regions here. Those 8 spaces, so to speak. So B intersects C. What are the same for these two? 1, 3. Now I want to find the union. A union B intersects C. So what are these two right here? When we bring them together, what does that look like? Well, everything that's in A, 1, 2, 4, 5. Everything that's in B intersects C, 1, 3. We'll list them all together. 1, 2, 3, 4, 5. So A union B intersects C will be represented by the following 5 regions. Region 1, 2, 3, 4, 5. we now want to determine, well, are those regions equivalent for the following expression? A union B intersect C. Why are we interested in this? Well, this is sort of like a distributive property, so to speak. Note that we're essentially just taking those two notations for union and intersect and switching them, all right? And that is even for our, or rather our parentheses, we're sliding them back, and we'll see here that for A union B intersect C, A union B intersect C, can we do that, right? We want to know, can we just take our parentheses and move them as we see fit? So let's go ahead and go to the right side as well, right? Let's go to A union B intersect C. And I'm just taking the parentheses and putting it around the A union B first. We're trying to determine, can we do that? Can we make it that easy? And over with the same bit of information we have here, I'll go ahead and go to the full screen. We first want to determine, well, what is A union B? With the following regions, A union B, the regions found in A, as well as the regions found in B. So we're just listing these. 1, 2, 3, 1, 2, 3, 4, 5, 6. Now we want to determine for A union B, what are those that are similar or that are the same in C? A union B, we now find the intersection between that and C. So we're looking at these two. What are the same elements or regions? 1, 3, 4. And that's it, right? So note here that we do not get the same 5 regions as we did in our previous expression. So we're trying to determine whether these two expressions are the same. And we just saw here that the left side expression is represented by our 5 regions, 1, 2, 3, 4, and 5. But for our right side expression, it is represented only by the 3 regions, 1, 3, and 4. So we have shown here that because the two Venn diagrams are not the same as we see here in our comparison, because they are not the same, we can say that the expressions are not equivalent or not equal. Now, what do we have here? Determine whether the following expression, and this is where my distributive property comes into play, so excuse me from before. Determine whether the intersection of A and B union C is equal to the union of A intersect B and A intersect C. So again, start on the left side, work your way to the right side. First, determine what is B union C. Oh, let's go ahead and work this one together. We want to determine first the left side, A intersect in parentheses B union C. And I'm just drawing this again because it's sometimes difficult for me to remember at times too. Our regions 1, 2, 3, 4, 5, 6, 7, 8, and mainly because I just erased everything over here. Regions for A, B, and C. For A here, 1, 2, 4, 5. And it's good practice. For B, we have here 1, 2, 3, 6. And for C down here, we have 1, 3, 4, 7. So let's take a look at first B union C. B union C brought together 1, 2, 3, 4, 6, 7. Then intersect these. A intersect B union C. So in A we have 1, and so do we have down here 2 and 2, 4 and 4, and that's it. Right. Is that the same as our last expression that we had, or rather the expression on the right? A intersect B union A intersect C. So again, to determine that, I'm going to do our image erase. Excuse me. Ooh, drop the eraser. I'm going to write out now the expression A intersect B. Union, we have there A intersect C. To determine the regions represented by this expression here, go to the full screen. Let's first find A intersect B. The things that are the same of A and B are 1 and 2. For A intersect C here, what are the same? 1 and 4. I want to find the union of these two, so I'm going to bring these two sets together. That is, all the regions will be brought together. 1, 2, and 4. We see here that the regions are the same for each of our two expressions. Each expression can be represented by the regions 1, 2, and 4. So therefore, right, we have determined that the left side expression, A intersect the union of B and C, is equivalent or equal to the union of A intersect C and A intersect B. And we see there that the image that we get for each was the same, right? The regions occupied 1, 2, and 4. So now we can say equivocally that these two expressions are the same. So one of our properties that we're going to see here, our properties of sets here, the first one we talked about is the commutative property, right? When we think about a commuter, we think about somebody that goes back and forth, maybe from home to school, from school to home. Commutative property means that we can move our sets around and get the same expression. That is, A intersect B is the same as saying B intersect A, because we're still looking at where both of these two sets are the same. A union B is the same as B union A. No matter which one you list first, you're bringing the same elements together when you unionize them. Our associative properties, when do they work for us? Well, previously we tried to move our parentheses and it didn't work. And that's because we had an expression that contained an intersection as well as a union. But note here, the associative properties are stated that if you have 3 sets and our only notation is the intersection notation, that is for our union intersection notation, if you have only intersections, then you can move those parentheses around. Likewise, if you have only unions, then you can move around the parentheses. At the end of the day, you're either going to determine what's the same for A and B and then C, or you're going to determine what's the same for B and C and then A. Likewise, you can determine all of the elements for A or B as well as C, or you can determine all of the elements for B or C and then A. Right? The way that you collect them or intersect will give you the same outcome. But what we just walked through here with the previous example represents our distributive property for our following sets. Note here that this is showing us a way to distribute an intersection over a union or distribute a union over an intersection. A intersect the union of B and C is equivalent to A intersect B union the intersection of A and C. Likewise, the union of A and the intersection of B and C is equivalent to the intersection of A union B and A union C. Question to you is, does the following expression have equivalency? Does the union of B and C intersect A, is that the same as the union of A intersect B and the intersection of A and C? Give you a moment there to take a look at that and see what you can come up with. Is this yes or no? The answer is yes, right? Consider our distributive property at the bottom, right? The first distributive property. All we did was take that expression and flip it around. And according to the commutative property, we can flip around an intersection. We took the A and the parentheses BUC, B union C, and we flipped them around. We are still going to get an equivalent distributive property thanks to our commutative property. So we have an exercise. The administrators of an internet music site plan to conduct a survey of college students to determine how the students acquire music. The administrators have decided to use the following Venn diagram to help tabulate the results of the survey. And here, note that we have our means for music are either through CDs, internet, or DVDs. So our example here, we want to shade in the region that represents the students who acquire music from CDs and the internet, but not from DVDs. So what are those regions that represent CDs and the internet, but not the DVDs? And then part B, we want to shade in the regions that represent the students who acquire music from CDs or the internet. Give you a moment there to pause the video and see what you can come up with. If you look at part A, students who acquire music from CDs and the internet, so there's an intersection there, but not from DVDs. Likewise, an intersection. And if you think about that, right, if CDs was set A, internet was set B, and DVDs was set C, to say not DVDs, that's C complement. So this would be A intersect B intersect C complement. We would see there that would be occupied by regions 1 and 2. We go to the full screen here. Regions 1 and 2 will be CDs and internet, but not DVDs. In this case here, DVDs contains region 1, so let's take that out. All right, just by our quick observation there, CDs and internet, well, that overlap there is going to be 1 and 2, but we do not want to include DVDs, and that's including 1. So part A is just region 2. Now, what about part B? It says CDs or the internet, right? We go back to part B. Show the representation who acquire from CDs or the internet. So in this case here, what's in CDs, what's in the internet? We're just going to list that out. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. CDs or internet, or potentially both, representing our union. Here we want to use set notation to describe the shaded region, so we're going to work backwards. What is the set notation that represents the shaded region as opposed to giving a shaded region for the set notation that they give us? So in this case here, right, elements that are in A but not in B, but also elements that are in B but not in A. So it's almost like we're just unionizing A and B, that is A or B, but A or B would also include the shaded middle. Now, if you negate A or B, that's going to be the outside shading, region 4. So in this case here, how can we get shading from only regions 2 and 3? Remember, for 2 sets, we only have 4 regions. The region in the middle is region 1. The region to the left is 2. The region to the right is 3. And then the outskirts is region 4. So how do we get regions 2 and 3? Well, let's consider there may be more than one answer. But one thing I'm considering is I want A to be included, but I want B to be included. But the fact that something is being left out means something is being negated. So let's start somewhere and see what we can come up with. I think we have an idea here. What about A, because we want A to be included, but we want to not have that. So if I don't want that, if I intersect it with B, well, that is in the middle. If I unionize it with B, well, that's both of the circles shaded together. So if I throw a complement here with a union, the complement of A means I'm going to shade everything on the outside, and everything on the outside unionizing B means that, well, the outside should be shaded if I throw a complement and a union together. But what if I switch this to an intersection? Well, what might this look like be? Well, A complement is everything that's not in A. B is everything that's in B. And if I bring them together, let's see here. Well, going off to the side, regions 1, 2, 3, and 4. A complement, everything not in A would be 3 and 4. Everything in B would be 1 and 3. So again, this would only have shading for region 3. How do we get the shading for region 2 as well? Well, what's B complement in this case? If I don't look at B, but rather B complement, I'm going to change 1 and 3 to 2 and 4. Now, once again, right, if I do this, their intersections together are going to be just for themselves, and that's going to be this outside shading. So take a moment here, as we've expressed, right, that there's possibilities for more than one answer, but we're going to have to be able to work through some trial and error to be able to get it and see what you can come up with here. So we found the expression that we are looking for here if we find the complement of A intersect B, intersect A union B. The key here, right, is trying to find a way to introduce that middle expression and then get rid of it, right? The middle expression is the intersection of A and B. So A intersect B is only region 1. But if I complement region 1, I get regions 2, 3, and 4. Okay, so I have regions 2, 3, and 4, and I just want to get rid of region 4. So in this case here, if I union something, I'm going to keep 4. So I want to intersect something that is not going to have 4. And something that's not going to have 4 is A union B. If I unionize A and B together, right, that is A union B are regions 1, 2, and 3. I just want regions 2 and 3 in the first place. So I got to find a way to get region 1 out of there. And the way that I do it is I intersect it with a complement of A intersect B. Again, right here, when you intersect these two sets, 1 is not the same, 2 and 3 are the same, 4 is not. So the only 2 regions here that are contained are regions 2 and 3. Thus, for our image prescribed here, we have the following expression to represent our image. We'll go to a second example here. All right, that's our expression, that's our image that we're looking for. Second example, But note here, right, for 55, we have our outside shading. Again, interesting that we just brought up this discussion that we want all of those elements that are not in A, that are not in B. We'll consider A union B for our example 55 here. We're only shading on the outside of our circle. Circle A, circle B, regions 1, 2, 3, and 4. Notice the shading here is only in region 4. So how can I find region 4? And it's using the union of A and B. That is, A union B contains the regions 1, 2, and 3. So if I complement that, well, what are the regions that are not 1, 2, and 3? Well, that's just region 4. So here we have our expression for number 55. For number 55, the complement of A union B. Let's go to our next example. Next example is going to involve 3 sets within our Venn diagram. So give you a moment here to pause the video if you'd like for number 57. We're shading everything that's in B and C. That is only in B and C, right? Not even mentioning A in this case here. So maybe just write this as not B intersect C, but B union C. For number 57, B union C will give us all of the elements that are in B. It'll give us all the elements that are in C. B union C. Next example, number 58. Number 58 gives us all the shading that's in C, and it gives us the shading that is overlapped from A and B. So we have some intersections going on here, and we have some unions, right? We're bringing everything from C along the ride. So maybe we're unionizing C, and then for A and B, it looks that maybe we are intersecting them, seeing where they overlap. Give you a moment to determine what you think you can come up with for number 58. As we were mentioning before the break of the video, we have all of C shaded, and we only have part of A shaded, part of B. So it looks like we will look to intersect A and B, and then unionize C to bring it together. That is, for number 58, if we consider what they shaded for us, they shaded regions 1, 2, 3, 4, and 7. We're trying to determine how can I find notation that will lead me to just those 5 regions. Well, consider A intersect B. Where do A and B intersect? It's right there at regions 1 and 2. Consider the set C itself to be regions 1, 3, 4, and 7. So if we unionize all of these regions together, if we unionize our intersection with C, we see here we're bringing together, right? We have sets or regions 1, 2, or regions 1, 3, 4, 7. So all together, 1, 2, 3, 4, 7. We have here the notation that represents our image. Remember what we just saw from the distributive property, A intersect B. When we unionize that with C, we can write this in another way. We will distribute the union over the intersection. That is, unionizing C with A, our intersection in the middle here, we unionize C with B. This expression is equivalent or equal to this expression here, right? According to our distributive property for 3 sets for our set notation. Looking at this last example here for 62, use set notation to describe the shaded region. Once again, we have all of the regions shaded for C, and most of the regions shaded for A. We're just negating that one little area that might be all the areas that are in A, C, and that one area where A and B overlap, right, that doesn't contain that little spot of A. So let's sit here and consider what might our notation look like. So I went ahead and shaded our active regions here. We have regions 1, 3, 4, 5, and 7 shaded for our example 62. I'll get that corrected here. Number 62. Give you a moment here to pause the video and see if you cannot come up with some notation involving sets A, B, and C. Maybe we introduce some complements, unions, intersections, involving parentheses, see what we can come up with for our example. The key here is kind of as before with number 58 is just, you see all the shading from C. So at some point we want to unionize C, right? Union C. So what are we trying to union with C? Well, we have just about everything with A. We have some stuff in B, but some things are not being included. And so that made me think to somehow work with A and B together and leave C on the outside as a union, because once again, everything in C is shaded. So, and again, it takes a little bit of practice, but we see here that maybe we come up with this notation. We have here that A intersect B complement will then be unionized with C. Well, let's determine again, what are the regions for A? It's 1, 2, 4, and 5. So I'll list out those regions for A. If region B has 1, 2, 3, and 6, I'm going to write out those other numbers, right? The numbers of 4, 5, 7, and 8. So where do they intersect? Which ones are the same? Well, it's 4 and 5. So A intersect B complement are regions 4 and 5. Now, when I unionize 4 and 5 with C, that is, C is regions 1, 3, 4, and 7, I'm going to write all these numbers together. 4, 5, or 1, 3, 4, 7. This becomes 1, 3, 4, 5, 7, which is what our shaded region gave us for number 62. So here we have A intersect B complement unionized with C. Once again, using our distributive property, we can write this in an equivalent form. A union C, A unionizes with C, and B complement gets to unionize with C. So either of these two are perfectly acceptable when trying to find set notation for our shaded region. This example here involves an art application regarding subtractive color mixing. Artists who paint with pigments use subtractive color mixing to produce different colors. In the subtractive color mixing system, the primary colors are cyan, denoted C, magenta, denoted M, and yellow, denoted Y. The following figure shows that when the three primary colors are mixed in equal amounts, using subtractive color mixing, they form the color black, denoted K. Using set notation, we state this as C intersect M intersect Y. In subtractive color mixing, the colors red, blue, and green, denoted R, B, and G, are the secondary colors. As mentioned previously, a secondary color is produced by mixing equal amounts of exactly two of the primary colors. So here in the following exercises, we want to determine which color is represented by each of the following. Assume that the colors are being mixed using subtractive color mixing. So here for number 50, we want to know what color is being created when we take cyan, intersect it with magenta, intersect it with not yellow. What this means here is we're not using yellow, but rather we're going to use cyan and magenta. And the color we get here for number 50 is blue, denoted B. Down in the region where cyan and magenta intersect and where yellow does not, we get the color blue. Number 51, we do not want cyan. However, we want magenta to intersect with yellow. Looking at the illustration, where magenta and yellow intersect and where cyan does not is red. Number 51, red. Number 52 says to take cyan, not magenta, and yellow. Where cyan and yellow mix and magenta does not, we get the color green, denoted G. We'll go to our next topic for difference of sets. Another operation that can be defined on sets A and B is the difference of sets, denoted A minus B. That is, right, if we are looking at A minus B, by definition, we get what is described below. A minus B is the set of all x's such that x is contained in A and x is not contained in B. If we switch that around, right, B minus A, then it would be all the sets or all the elements that are in set B and not in A. In this case, A minus B, what's in A and what's not in B. The following example asks us to find A minus B, where set A contains 1, 2, 3, 7, 8. Set B contains 2, 7, 11. Well, to find A minus B, what we're going to do is look at the elements that are in A on the left side. 1, 2, 3, 7, 8. Are any of those elements also in B? If they are, we need to remove them from A. In this case, we see for set B, it contains elements 2 and 7. Those two elements are found in A. We will remove 2 and 7 from our set A. We don't have to worry about 11 because 11 is not contained in A. So A minus B has us look at set A and remove those elements from set A that we also see in set B. Removing 2 and 7 leaves us with 1, 3, and 8 for A minus B. What would you get for B minus A? B minus A says look at 2, 7, and 11. We've already noted that 2 and 7 overlap, right? They're found in both sets. Therefore, B minus A would require us to remove the 2 and 7 from B, leaving us with only 11. B minus A consists of the single element 11. Given the following universal set, numbers 1 through 9, that's natural numbers 1 through 9, set A 2, 4, 6, 8, set B 2, 3, 8, 9, find B minus A. Now, thinking ahead here, we're going to see a couple of different examples to work with right now. They give us a universal set along with sets A and B. So it suffices to say we might want to go ahead and find A complement as well as B complement. So I'm going to go to the full screen. Find the elements for A complement. Just look at the universal set and take out 2, 4, 6, 8. Same for B complement, take out the 2, 3, 8, 9. First example was to find B minus A. Here's how we'll do it. It's B minus A. So we're taking out some things that involve A, but we're starting with B. B is 2, 3, 8, 9. Take away anything that's in A that overlaps with B. So note here, and think about if you want to do this, write out all the elements of B, 2, 3, 8, 9. Take away whatever's in A. A contains 2, I have it written, I need to take it away. A contains a 4, it's not down here, I don't have to worry about it. A contains a 6, it's not down here, I don't have to worry about it. A contains an 8, it's right here, I need to take it away. So B minus A leaves me with 2 elements, 3 and 9. I start with the elements in B, and I take away any of the elements that I find in A. So if I switch this and did A minus B, starting with A contains 2, 4, 6, 8. I'm taking away whatever's common from B. B contains a 2, I'm taking it away. And we saw again, right, B contains an 8, I'm taking it away. So A minus B would be 4 and 6. Let's see here what the slide suggestion suggests for some additional examples. We found A minus B. Let's take a look at A minus B complement. Let's take a look as we switch that around, B complement minus A. A minus B complement, so we're starting with A, 2, 4, 6, 8. I'm going to take away whatever's common from B complement. B complement contains a 1, but this does not. B complement contains a 4, I'll take it away. B complement contains a 5, this does not. B complement contains a 6, I must take it away. B complement contains a 7, this does not. So A minus B complement will just be the 2 elements, 2 and 8. To find now B complement minus A, and to subtract to find the difference, start with B complement, that is 1, 4, 5, 6, 7, and take away any of those elements that are also found in A. A contains a 2, this does not. A contains a 4, so does this, we'll take it away. A contains a 6, so does this, we'll take it away. A contains an 8, this does not, so we don't worry about it. And we're done. We've exhausted all the possibilities of taking away elements from A. So B complement minus A is 1, 5, and 7. See here now what some other examples we could do to finish off with the sets that we have. How about now A complement minus B complement? And then we'll look at A complement minus B as well. So A complement minus B complement, go back to, looking at that example right there. We've already found 4 of these different sets, so go ahead and take a look at a few more. And You know what? We'll go ahead and jump to 76 before we get to 75, and it's A complement minus B. Therefore, we'll go ahead and find that other one as well. If we switch this around, B minus A complement. Just trying to show all possible examples that we can. So we'll go back to, see, start, if we're doing A complement minus B, start with A complement, 1, 3, 5, 7, 9. Take away B. Take away a 2, take away a 3, take away an 8, take away a 9. So A complement minus B, 1, 5, and 7. What about B minus A complement? Start with B, 2, 3, 8, 9. Take away A complement, take away a 1, take away a 3, take away a 5, take away a 7, take away a 9. B minus A complement contains the two elements 2 and 8. Now, notice here, if you might see some connections, maybe some overlap. As I see here, I have the set 1, 5, 7. I have the set 1, 5, 7. I have the set 2, 8. Right? I have the set 2, 8. I don't have any connections yet for this. Now let's consider throwing some complements on both of them. Right? In each of these examples, we've had one complement up here, or no complements. Let's do two complements. A complement minus B complement, B complement minus A complement, and see if we don't get some connections between these two and these two. I bet we do. A complement minus B complement, start with A complement, 1, 3, 5, 7, 9. Take away B complement, take away a 1, take away a 4, take away a 5, take away a 6, take away a 7. So A complement minus B complement contains the two elements 3 and 9. What about B complement minus A complement? Start with B complement. Start with 1, 4, 5, 6, 7. Take away A complement. Take away a 1. Take away a 3. Take away a 5. Take away a 7. Take away a 9. So B complement minus A complement contains two elements, 4 and 6. So now we're going to be able to make some generalizations here. We've established a connection between our following examples. And what is that connection? What is that example? Is that, well, A minus B is going to be equal to B complement minus A complement. That is, B minus A is going to be equal to our A complement minus B complement. So something that we do want to note here, that we get these equalities now for our different sets as well. I will have you, if you haven't already, pause the screen and have these written down. We will now erase this and write out our generalization for any two of our sets here. These finite sets that we're working with, we now see that for our difference of sets, A minus B, that A minus B is equal to B complement minus A complement. Likewise, if I switch this around, if I switch around the A and the B, I switch around the B complement and the A complement. That is, B minus A is equal to A complement minus B complement. Now, what else were we establishing for our last few expressions? And that if you switch around the two here, throw the complements on, and you'll get the remaining expression. That is, if I have A complement minus B, I'm going to flip these two around, but then I'm going to give these the complement of one another. That is, if I take A complement and move it to the second spot, it becomes A. If I take B and move it to the first spot, it becomes B complement. A complement minus B is equal to B complement minus A. A minus B complement would be equal to B minus A complement. We have here, I believe, right? Those are our four. So for our difference of sets, we get the following generalizations as well.